Okay, so we're continuing today with volumes of solids of revolution. We're going to start to kind of do a little bit with shifting the axis and looking a little at what happens when you revolve around the y-axis, but for the most part, I think everything will be very similar to yesterday. Fundamentally, I want you to remember the idea that your formula is integral from a to b of pi times your outer radius squared minus pi times your inner radius squared dx, okay? And then if I change things to be in terms of y, it will be a y value for each of the a and b will be y values, and then our functions will have to be in terms of y, and dy will be our integral. But we'll get to that when we get to our example there. So it says, consider the region bounded by the curves x squared and x cubed. Sketch the region bounded by the curves, etc., and find the volume, what happens when you revolve this around the x-axis. Okay, so first things first, I've sketched my region. Next thing you'd want to find are what are the intersections. So you can see these intersect at 0 and at 1. Okay, so we want to be imagining that this is being revolved around the x-axis. So as I mentioned in yesterday's lesson, you want to think about reflecting this figure over the x-axis and imagine these little circles or donuts that are being formed, or washers if you want to think of them like that you're now adding up as you go through your region from 0 to 1. So your integral is going to definitely go from 0 to 1. Now the tricky part with this one is that the outer radius and inner radius might not be exactly what you'd expect. Most people would think that x cubed is going to be a bigger value than x squared, but on the interval from 0 to 1, think about doing 1/2 squared. Think about doing 1/2 cubed. 1/2 cubed actually comes out to be 1/8, which is smaller than 1/4. So actually the inner function is the smaller one, x cubed, and your outer function is actually the bigger one, x squared. Okay, so on this interval, again, you're going to do pi times your outer radius, which is x squared squared, minus pi times your inner radius, which is x cubed squared dx. Feel free as you go through your problems today to use f of x and g of x, or y1 and y2 to represent them, but just make sure that's clearly communicated on your page, and be careful when you type in your calculator. And when you do this, you'll end up finding out that this comes out to be 0.180 for the volume of that figure created when that's revolved around the x-axis. So if you take a look at part A, okay, like the additional part of this question, it says, how do you think that the volume would change if we rotated this region instead of around the x-axis, around the line y equals -1? So let me redraw a sketch of what this region looks like, okay, the original one. It looks something like this. Okay, now instead of revolving around the x-axis, now we're going to revolve around the line y equals -1. Okay, so as I mentioned before, I think the first thing you should do is try to draw like what your region looks like if you were to reflect it over the line of rotation. It's not going to be perfect. You will see that fundamentally your formula is still going to be the same, because once again, you're still dealing with washers. You still have the same intersection point, so it's still going to go from 0 to 1. It's still the same idea, adding up all these little disks, so it's going to be pi times whatever your outer radius squared is, minus pi times whatever your inner radius squared is, dx. We just have to think about how do our outer and inner radii change as this line gets shifted down. So you can see from where the original radius had looked, you can hopefully see that this radius is bigger. The question is how much bigger, and that really has to do with whatever line you're rotating around. The line y equals -1 means that you're actually adding one whole extra unit to each radius. Okay, so it's the original function value plus one extra unit. So that's how we're going to end up finding out that it was our outer radius, which was x squared, and our inner radius, which is x cubed. But each one this time is going to be added by 1 because of the fact that you're revolving around the line y equals -1. Now that might seem confusing for some people, because you're like, well, why am I not minusing 1? Again, the whole idea is that initially look at the size of your radius, look at how much bigger it is as you move that line down. If let's say you move to the line y equals -4, then each of these would be +4 instead of +1. Okay, so it all has to do with how far is that line moving down. That's how much you have to add to each radius. You'll notice that the outer and inner radius are still the same, like that hasn't changed, nor is the cross section going to be any different. You're still adding up all of these washers. Okay, so if you go ahead and you plug that in your calculator, you'll find out that that comes out to be 0.703 for the volume of that region as it's revolved around the line y equals -1. Okay, so let's take a look at one when we go around the y-axis, because we haven't really done one like that just yet. It says, consider the functions y equals cube root of x and y equals x over 4, where x is greater than 0, as you can see in the diagram to the right. Find the volume of the solid as it's revolved around the y-axis. Okay, so same idea of what I've mentioned before applies. Take the line that you're revolving around, take the figure that you're revolving, and try to draw it being reflected over that axis. It's not going to be perfect, obviously, again, it's just a sketch, but you can see I'm still making these little washers or discs or whatever way you want to think of it. The biggest difference now, though, is that everything has to be in terms of y. Okay, if you're going around the y-axis, all in terms of y. That means that you have to have the y values of your intersection. So this y value would be at 0. This y value is going to be at 2. Okay, you can see right here on that diagram. So my integral is going to go from 0 to 2. I also need to have my functions expressed as functions of y. So if you take y equals the cube root of x, cube both sides, that comes out to be y cubed equals x. One of these functions is y cubed. Okay, so maybe I'll put them in a different color. This function here is y cubed. And then if I do the other one, this was y equals x over 4. Cross multiply, this comes out to be x equals 4y. So that means that the other function we're dealing with is 4y. And you're still going to deal with the same idea, like what makes your outer radius? What makes your inner radius as you revolve around the y-axis. So hopefully you can see here that it's actually the linear function that's creating the outer edge of our function here. So that's how we're going to end up getting that our outer radius is 4y and our inner radius is y cubed. So we're going to go and plug that into our formula. Again, same idea. It's pi times the outer radius, which is 4y squared, based on pi r squared, minus pi times the inner radius squared, and you're going to set everything up to be in terms of y. Now, I would say probably with something like this would be one of those questions where it would be like set up but do not actually solve. But if you had to go and plug it in your calculator, you would actually plug it in with these as x's, even though everything is set up in terms of y. If you do this, this comes out to be 76.595, if you want to just approximate it to 3 decimal places. All right, so let's take a look at one that is actually stemmed from an AP question, just to get an example of one of those done, and then I'll let you guys go off and practice on your own. So it says, let f and g be functions defined by f of x equals, this function right here, and g of x equals this function right here. This one 100% would be a calculator-based question, okay? So this is not something you'd have to do by hand. As I've mentioned before, whether you're finding area or volume, I think the first thing you should do, go in your graphing calculator, plug this in as, let's say, y1 and y2, or whatever way you want to do it, and find the intersections. Notice the window they're giving you, you're only going from x equals 0 to x equals 2, and y equals 0 to y equals 4. So if you want to like shorten your window in to get a picture that looks more like what you see here, you can. If you just graph it on a standard window, it might not look the same to you. Okay, so we want to find the sums of the areas of R and S. You first have to find this intersection here. So graph this in your calculator, second, trace, intersect, and you'll see that this intersects at 1.033. Okay, so as I start setting this up, you'll notice that in this problem, it's actually my g of x function. That's my upper function initially, but it becomes my lower function in region S. And then f of x is my lower function, but then eventually becomes my upper function. Obviously, as I set up the integral for these two areas, I have to be careful of what's the upper and lower. Now let's go back to area for 1 second. A lot of people make mistakes with area because they start throwing pies and squaring things, but that's only when you're dealing with volume. If it's area, the area is always integral of upper minus lower. Okay, so you're going to integrate from 0 to 1.033. That's the first region. Your upper function is g of x, your lower function is f of x, and then you're going to add the integral for the second region. So integral from now 1.033 to 2, you can see right here, 2 is the end of that region. And again, the upper and lower change in this second one, f of x minus g of x dx. So if you need to pause for a second. When you plug this in your calculator, keep in mind this was something like y2 minus y1 and y1 then minus y2 for the second half. So be careful to make sure you type them in the right order. And when you're done, you round to 3 decimal places. This comes out to be 2.004. So part B, find the volume of the solid generated when we rotate just R, okay? So pay attention, this is not that whole combined region. You're just rotating one part of it. Rotate R around the x-axis. So as I mentioned before, I think you should sketch it, okay? So let's say this is our region R. Draw R being reflected over the x-axis, and then think about the fact that you're making these washers. Okay, thankfully our bounds are going to stay the same as the bounds we used for the area of R. That's 0 and 1.033. Now I need to have pi times my outer radius. What's making the outside edge? Remember, g of x was the upper function when you were in this region, and f of x was the inside function. So it's our outer radius is going to be g of x, okay, squared, sorry for that extra parentheses, minus pi times f of x squared dx. Okay, when you go and you plug that in, that comes out to be 16.256. Okay, now keep in mind what change is happening in the next one. You're now rotating S. You're not rotating R anymore. Okay, so notice that when you're in S, F and X are F and G are switched. You're also not rotating around just the x-axis. You're rotating around the line y equals -4. So think back to what I mentioned earlier in this lesson. So I would start like I mentioned before. Sketch what your region looks like. Okay, so here's your region S. Draw that region being reflected over the x-axis. Okay, actually, I'm sorry. Let me rewind that for a second. You're not reflecting that over the x-axis. You're reflecting that over the line y equals -4. So let's say that this is what our thing looks like. Here's our region S. Let's say, and I'll even move this down closer so I get a better picture. And let's say that this is now my line y equals -4. Okay, so you have to think about how is this going to change each of these inner and outer radius. So normally the radius would have been something like here, right? That would have been what your normal washers would have looked like. But now you're extending so that your inside circle looks like this, and your outside circle looks like this. Each radius is getting bigger by 4, okay? So again, watch for that opposite relationship that's here. Now, what are the bounds of the region S? Same bounds as we used for the area before. Integral from 1.033 to 2. It's going to be pi times whatever your outer radius is squared minus pi times your inner radius squared dx. This time, if you notice again, looking up at S, it's your f of x that makes the upper edge and your g of x that makes that lower edge. This is f of x and this is g of x. So it's going to be f of x with some sort of a change and g of x with some sort of a change. As I mentioned before, the fact that you're moving the line of rotation down 4 units, you're actually going to be adding 4 to each of those radii. Be extremely careful when you plug this in your calculator. I would definitely, again, imagine it's going to help you if you use things like y1 and y2, watch your parentheses, and then eventually when you go through and you do that calculation, you'll find out that that volume comes out to be 40.8397, or 40.